ask questions to all the panelists. So please get ready to ask some good questions for the final discussion at 6:30. Now it is my pleasure to introduce Zhi-Qin Xu. I hope I pronounced correctly. So please go ahead. Please start your presentation. I'm very much looking forward to it.
I share the screen. So can you see the screen?
Yes.
Okay, so I want to thank Wolfram for inviting me here to talk about our recent talks and our recent works. And part of my talk is very similar to what Wolfram has talked about. So this work is mainly work, a joint work with Zhang Yaoyu and Luo Tao and some of my colleagues. So we know that neural network has a very great expressive power. Single hidden layer neural network can almost fit any function, but this is not enough because what we want is not only fitting, we want generalization. So now let's take a look at the traditional generalization theory. Suppose we are going to classify two types of data, and we may use a linear function and end up with not a good either training error or generalization error. And if we use a more oscillated curve, yes, we can classify the training data very well, but we can incur very large generalization error. So traditional generalization theory says that if you increase the model complexity, you may decrease the training error, but at the same time, after some point, you will increase the test error. So there will be a generalization gap. You may choose an optimal complexity, such as this function can better classify the data and also generalize well. But this may not apply in deep neural networks. Since 1995, there is a generalization puzzle that neural network can generalize rather well, even the number of parameters is much larger than the number of training data. So in 2016, Zhang Shiyuan and their colleagues shows an experiment that if you use a very large networks to fit like Zhi-Qin data, you can get a very good accuracy and also not a bad test accuracy. Actually, many people has already knew this something result like this, but this work has systematically performed experiments to confirm this puzzle. So this attracted a lot of attention. So we try to understand why from the training process of neural network. Let's take a look at an example of one-dimensional function fitting. So suppose we use a neural network to fit this red curve target function. And the blue curve is the output of neural network. This will be a movie, and each frame will be several training steps. So as we can see that the neural network can capture the landscape of the target function very quickly. And after some time, there is more and more detailed structures. So you will learn from landscape to detail. So naturally, it will be easy to use frequency to describe this landscape and detail. So we perform Fourier transform of both target function and also the neural network output. This red curve is the FFT of the target function, and this blue curve is the FFT of the neural network output. Similarly, this is also a movie, and we can see that the neural network captures a low frequency very quickly, and after some time, it captures more and more frequency. So we conclude from very simple experiment that and frequency principle that neural network learns data from low frequency to high frequency. And not only us, but also many other works has shown experiments that this frequency principle is quite universal and also some theory. So we can apply this frequency principle to understand the generalization puzzle. So in these experiments, and we know that neural network can perform rather well in like MNIST or Zhi-Qin imaging classification task. And if we perform a Fourier transform of this classification function in some direction or projection, this Fourier domain function into one dimension, we can see that in the image classification task, the target function actually is low frequency dominant. And the neural network indicated by this blue dashed curve is also low frequency dominant. It prefers low frequency. So you can learn low frequency very well, but the high frequency part, the training data and the test data already has some different, and the neural network cannot well learn this high frequency, but it's not important. So the neural network can generalize very well in such low frequency dominant function. But for another function, this function called a parity function is defined on -1 and 1 in each dimension. And the output is the product of each dimension. So it's called a parity function because it's equivalent to account the number of -1. If it's even number of -1, its output is 1. Otherwise, it's -1. In function, we change input, output will have a significant change, so a high frequency function. In such a case, the neural network will capture the false low frequency due to the sampling and will have a very small portion of high frequency. So the finally learned function, the blue curve, is very different from the target function. So in this case, the neural network has no generalization ability. So this example shows that we start from frequency perspective. We can understand it qualitatively, but not quantitatively understand why the neural network can generalize well in some tasks, but not in other tasks. So we have a very simple conclusion that neural network learns data from low frequency to high frequency, or simply, if no need, the neural network will add no more frequency. This resembles the Occam's razor. However, this frequency principle is too constrained. We found that it's not able to capture all details. So here is an experiment. Suppose we use a two-layer neural network to fit a one-dimensional function, only have 4 data points as the training data. We used a different initialization scheme, and we found that all these 3 cases, they follow the frequency principle, that is from low frequency to high frequency, but the function they finally learned are very, very different. And we want to look into more detailed things about this learning process. So we check the weight of neural networks after learning. So we care about the input weight and also the amplitude of each neuron. Since we study the ReLU neuron, so its amplitude of the input weight is not important because it's a homogeneous function. We can take its amplitude outside the function. So we only care about the direction of this input weight W, and also the amplitude is the amplitude of A times the W. And this W, the direction of W, if we only care about, if we only do experiment in one-dimensional input, then this W actually is a two-dimensional vector. Sorry, it's a two-dimensional vector, the input weight and also the bias term. So we can use an orientation angle to represent this input weight, the direction. So the x-axis is the orientation and the y is the amplitude. And in the linear regime or the NTK regime, we can see that the red is the green one is the initialization parameter distribution, and the red one are the parameters after training. We can see that in the linear regime, the initial parameter and the final parameter are very close. This is consistent with what we have learned from linear regime. And in the mean field regime, that the initialization is small. We can see that after training, the parameters, they have some condensation, but not extremely condensed. The orientation has only condensed at some few values, but still have some other values at some orientations. If we continue to decrease the initialization magnitude of parameters, we can see that after normalization, almost all the parameters, the input weight, they condensed in 2 directions. So it's a very, very strange phenomenon when we observe it at the first beginning, and we try to understand why. But before we understand why, we want to ask what condensation benefits, or why the neural network, why when a neural network want to condense. So suppose this is a neural network with random initialization, and the weight are randomized at the initial state. After some training, there's a condensation happening. So what's the condensation? We draw a cartoon here. That means for extremely case, they condensed in only 1 direction. That means for each input neuron, its input weight to every hidden neurons are exactly the same. So this neural network actually is reducible neural network, as called in the Burfen's talk. So we can actually reduce this neural network into a very small effective neural network. That is only 1 hidden neural network. So its effective network is very small. So now let's go back to this puzzle. We ask the question, is there really so many effective neurons in large networks? For example, in this very simple case, although we use 10,000 neurons in this example, but actually 2 ReLU neural network, 2 ReLU neurons actually are enough to express this, this function. So we can see that after training, the neural network actually converge to a very small effective neural network. We want to ask how general of this phenomenon exists in training neural networks. So we study the initialization in different, we study which kind of initialization can finally converge to such condensation phenomena. So we study a 2 neural network with ReLU activation function and infinite with limit. So the problem can be clear and very easier to study. So we study this two-layer neural network with parameters alpha AK and WK here. And AK and WK are initialized from a Gaussian distribution with some standard deviation. And we normalize this gradient flow for each parameters by their magnitude and initialization. And there are three parameters, and we don't care about how fast the neural network evolve. So we only care about the final state. So we can eliminate the variable of time. So we only need to care about 2 parameters. So we found the 2 scaling parameters. And these 2 parameters actually can control the initialization enough. So we found that at these 2 hyperparameters, we can summarize some many current studies of infinite with limit. For example, in this blue part is called a linear regime. Their behavior are very similar to NDK, and at this critical boundary line is very similar to the behavior of mean field. And at this green part is another regime. We call it condensed regime, because in this regime, neurons will condense. So here's an example of MNIST data set. And we also use 2-layer neural network. We found that at this regime, when we increase the neuron numbers, when the neural number goes to infinity, the condensation is more and more clear. So the condensation is a very kind of universal phenomenon in the neural network, especially we observe in this infinite with limit. So this phenomenon actually gives us another result that if no need the neural network in some initialization regime, we'll use normal effective neurons. So it also resembles the Occam's razor, small net or maybe effective small network is effective. So now let's get back to this picture. The original neural network is very large, and actually after learning or training, the neural network is very similar to a two neural network. So why we need to use so much energy to train a very large neural network? Why we don't just use a two neural network? So what's the difference between these two kinds of neural network? Is there any similarity or difference? So we study their similarity and difference in this talk from loss landscape. So we know the loss landscape is very complicated, just like if we have a very complicated traffic. And if there is no light, this road will be very crowded. And if there is a traffic light, and every car or people goes under the rule of light, so everyone can run smoothly. Similarly, in the loss landscape, it's very complicated. But actually, in the practice training, we found the training, it seems not so complicated. It seems there's some guidance in the neural network, and the training can be easy. So who can be a traffic placement in the loss landscape? Now let's take a look at this example. Suppose the training may start from an initial state to a final stage. But if during the trajectory, you have some saddle point, and this saddle point will attract the training trajectory, but it also will slow down the training. This is a characteristic of the saddle point. Now let's take another viewpoint for training process. Previously, we looked at it at a Fourier domain. Now let's just look at a spatial domain. So the target training data is the blue dots, and the network is the red solid curve. So we found that after some training, its output is very similar to a single neural network's optimum. And after a long-term training, its output is very similar to the 3 neural network optimum. And we are wondering why it will go through this like single neuron optimum or 3 neuron network optimum. So we take a look at its training loss. This is the training loss of this 500 neural network. So we can see that during the training, it will go through a plateau. At this plateau, the training is very small, and the neural network output here, indicated by this red solid curve, it almost overlaps with the optimum output of the 1 neural network. So it seems that in a 5 neural network case, the optimal output of the 1 neural network is a critical point or a saddle point in the 500 neural network. And similarly, after long training, its output is similar or very similar to this 3 neural networks. Usually we define critical point in a parameter space. If a parameter is a critical point, if the gradient of the loss with respect to the parameter at this point is 0. However, in these examples, we can consider in another way, the critical points somehow is related to the output. In some sense, we can define the critical points by the output, but not the parameters. If in this way, we can see that the critical points of wide neural network should contain or should see the critical points of narrow neural networks. We can have a conjecture that the training of a large network will go through the small networks optimum to large networks optimum. It has some order, just like frequency principle from low frequency to high frequency. So it will go from initial and then goes to some 1 neural network optimum and 3 and so on. So this is our conjecture. So, but to have this conjecture stand, we actually need a basis. That is, in the loss landscape, the optimum function of small network is a critical function of large network. And we train more neural networks with different width. So we can see that almost all neural networks, they can go through some plateaus at the same, almost the same loss value. And their output at this point actually very similar. So this further confirms our conjecture. So we propose an embedding principle that is the loss landscape of any network contains all critical points of nano networks. Okay, we can use this simple example to explain this. Suppose for a for one neural network, its loss landscape may be like this. And when you add one more neurons, this point will change from local minimum to saddle point. And its local minimum or global minimum is a 1 with smaller loss. And if you add one more neuron, and this point will become another saddle point, and its optimal point will have a lower loss. So how to prove this? This is almost exactly the same as Berven's talk, but this actually in our work, we inspired by this inverse process of the condensation. In the condensation, we have a lot of neurons and they condense. But here, to prove this embedding principle, we can split a small neural network to a large network. Here's an example of adding one neurons. And if you want to add more neurons, you can consist of multiple steps of one step embedding. So in this case, we want to split this black neuron. So we split this neuron into two neurons, and the input weights are copied, and the output weights are split by a ratio of alpha. And this ratio is applies for each neuron to ensure the criticality preserving. So we have this theorem. Under one-step embedding, we have the output of the nano neural network is the same as the wide neural network. And if the parameters in the nano neural network is a critical point, either saddle point or local minimum or global minimum, the parameter embedded from this nano neural network is also a critical point, but maybe in different types. So this is an inverse of condensation. So this is one-step embedding is very similar to previous work like Fukumizu and Amri and also Simsek's work. And we also proposed recently, we also proposed a more general embedding, not only one neuron added by one neuron by another, but added by a bunch of neurons. So here's an example. For example, in this case, we split the neurons in the previous layer and also in the next layer into several neurons. In this case, they are split into 3 neurons. So in this case, to preserve the output, so the input from the previous neuron to the poster neuron, their coefficient should have a summation of 1. This is to preserve the output. But we also need to preserve the criticality. So we can compute the gradient of the loss function with respect to the output of this neuron. This will be consist of 2 parts. One is the blue neuron, the other is the green, the red neuron. And similarly, after splitting, the gradient of the loss function with respect to this purple neuron should also consist of several parts, the blue part and also the red part, to ensure that the summation of all these parts equals to 0. And what we know is that this 2 parts summation is 0. So if we have some coefficient of the summation of this blue part, their coefficient should be same. That means we can compute the gradient of the loss function with respect to the output of this neuron, by 2 parts, and we can take out their coefficient for each part, blue part and the red part. And to ensure this summation is still equals to 0, we need to require that the coefficient for each part should be the same. So we can take out the common factor, this beta, and then this summation inside can be equal to 0 based on the condition of the criticality in the previous smaller neural network. And we can discuss the dimension of the critical manifold on loss landscape after embedding from a smaller neural network to k-neuron wider neural network. At least you will have a k-dimensional critical affine subspace. Just like here, you have a 1 point critical point after embedding, you will be 1-dimensional, and after 2-step embedding in the first 1-step embedding, you will have a plane. So in wide network, the simple critical function, that means it can embed it from a more narrow neural network, can form a higher dimension manifold. So here is a cartoon that says if in 500 neural network, if this critical point is embedded from one neural network, at least it has 499 dimension. And when the critical point is embedded from a larger network, its manifold will decrease. So this is a partial order for multiple layer neural network. And for the general embedding, we don't have an exact estimation of the dimension, but we have some guess. That is, K is the total neurons added in the added in the nano neural network, and KL is the number added in the else layer. So this is a guess of the dimension. And we have a theorem says, this is all very similar to previous Irfan's talk, that the number of positive, 0 or negative eigenvalues is in the Heisen of the nano neural network, of the large wide neural network, is no less than the counterparts of the nano neural networks Hessian matrix. And we from some experience show degeneracy in 2 neural network and to learn the data. And after learning, all eigenvalues of the Heisen are positive. That means it's a local minimum or it's a global minimum. And after we embedded this neural network to 3 neural network, there will be 1 eigenvalue, very, very small. We can regard it as 0. And also, we found that an eigenvalue actually turns from positive to negative. We have a negative eigenvalue, and we embedded it to wider neural network. There will be more negative eigenvalue. That means that in larger networks, the critical points may have more descent direction. That may explain why wider neural network is easier for training, because there may be no local minimum, but saddle points, and has more and more descent direction. But we are also thinking about, is there any true battery critical point? That means at this for this point, no matter how many embeddings, it always local minimum, but do not have any negative. It's possible, but we have this theorem. If we decompose this Heisen matrix into 2 parts, and this decomposition is very natural, if the second part does not equal to 0, and you will have a embedding that after embedding, there will be a negative eigenvalue. So you will turn into a strict saddle point. So finally, I will use a cartoon to summarize our understanding from this hierarchy structure of loss landscape. During the training neural network, you have initial parameters, maybe very chaos, and the loss landscape is very complicated. But during the training, you have some guidance from the nano neural network's critical point. Maybe first you will go to one neural network's critical point, then to the two neurons critical point, and so on. And maybe sometimes you will just pass through this some middle critical point and directly go to some larger neural network. And finally, you arrive your destiny. And we also show that this condensation is also can be easily observed in neural network with training on MNIST data set. In these examples, we show that a lot of neural networks, their directions has a very high correlations. Their directions are very aligned together. So we can prune the neural network and get a very similar result. So finally, I want to use this picture to conclude my talk. The neural network's loss landscape is not as easy as a convex function. Also, it's not so complicated as a protein folding loss landscape. It may have some spatial hierarchy structure that enable us to train it well. So this will be my final slides. That is the embedding principle. The loss landscape of any network contains all critical points of all nano neural networks will serve a basis for the condensation, a path for gradually increasing the number of effective neurons. Okay, I will end my talk here.
Thank you very much for this great talk, very nicely presented. We have some questions from the attendees. Do you want
I can see it. Yeah, I can read it. I can read it. What about the weighted decay regularization? Yeah, so far we don't study any regularization. We believe that if you add some regularization, you will change the loss landscape structure. But so far I cannot answer this question. Okay. Like the feature distribution shown in the condensed regime, I assume that's for two-layer. Yeah, it's for two-layer neural network. Is there a related empirical evidence of condensation of and deeper neural networks? Yes, we have a recent work in, you can check it in my homepage, that we can observe this condensation at a very deep and also at the residual neural network. But one condition is if you want to see a clear condensation, you need to require your initialization be very small. Okay. In case there is no any finite critical points, can we still use narrow neural network? In case there is no any finite critical, there is no any finite. What's the meaning of no any finite critical points? There could be. Actually, don't understand what's the meaning of no finite. What's the meaning of finite critical points? Maybe you can say more about this. Yeah, you also, I may get your point. Actually here, I don't require this critical points to be global minimum. I only require this point is a critical point. So if you have a very nano networks, even one neural networks, you can have critical points. Definitely you will have critical points because you have this global minimum. Maybe this minimum maybe not able to well fit your curve or your data, but it's the minimum. So you can use the nano neural network, if I understand it correctly. Does the objective function play a role in shaping the loss landscape together with the time? So far, our results are rather general for the loss function. So for the objective function, but for the cross entropy, there will be something should be very careful, because for cross entropy function, if you want to get the global minimum, you need to go to infinity training time on the weight should go to infinity. But for the critical points, not a global minimum, the result should apply. You mentioned the mean field. You mentioned the mean field parameterization and NTK parameterization in phase diagram. Where does the standard parameterization lie? Okay, I can show this picture. So standard may be something like Davia or like Lecoin initialization. If you increase the number of neurons goes to infinity, this initialization scheme actually lies in a linear regime. Does the choice of the loss function also impact or not? Yeah, we tested some loss function like x square, no, x4, x to 4 times x4, x to exponent 4, not a quadratic loss function, very similar results, but it's not easy to train. And during our proof, actually, it's not so, this hierarchy structure, it's not so related to the choice of loss function. If you want to prove some, about some this eigenvalue things, this Heisen, if you require, you may require some derivative condition for activation function. Yeah, this is my answer. And is there any question in the panel?
Yes, I think there's some questions in the panel. Berfin, please go ahead.
Yeah, thanks a lot for the very nice presentation. I had a question about the saddles and with the negative eigenvalues, because you really emphasize the number of negative eigenvalues. But what I gather from non-convex optimization literature is what matters is the most negative eigenvalue more. But I wonder your intuition on this.
Oh, you mean the number of negative eigenvalues, right?
I was thinking about the other figure with red dots and blue dots.
Oh, this one. Oh, sorry. This one, right?
Mm-hmm.
This is a, okay. This shows the experimental result that there will be more negative eigenvalues. But theoretically, what we can prove is the number of, this is the only thing we can prove so far. And this is the result of experiment. And we actually don't understand in which case or in what condition there will be more and more negative eigenvalues. Yeah, we are not so clear for this. But we can show that if you have this condition, if you have this, if you have this condition, the second part, this part, is not equals to 0. You can construct a critical embedding that after the embedding, there will be at least one negative eigenvalue. So this, we need this condition.
Clément, you have a question?
Yes, thank you very much for your talk. Just a small question about the number of effective neurons that you see. I mean, you see patterns in the way the effective number of neurons increases along the training. I mean, you went from 1 to 3 in your example, for instance. So you have some jumps. You
mean like this?
Yeah, like this. But so this is on a fairly synthetic example, but do you see kind of patterns in the way this number increases?
We in some real experimental data like this, like this one, we actually can see at the first beginning you only condense at a very few neurons, and during the training there will be more and more neurons. Yeah.
Of course, but I mean, in the way, I mean, you increase one by one usually in these examples.
No, not one by one.
No.
As I mentioned, you can just go bypass some middle stage, and usually it bypass some middle stage. Like in the previous examples, it directly go often. It directly goes from 1 to 3.
Right. So, but you usually jump by 2 or a few?
No, we don't know. This dynamic process, actually, we don't fully understand.
Oh, thanks.
Great. If there are no more questions, we're perfectly on time. Thank you, Zhi-Qin, very much for the talk and answering all those questions.